Okay, hello everyone, welcome to the first presentation from the Algebra 2 module on coordinate geometry. And coordinate geometry was something which first came about thanks to a very famous person called René Descartes. That's why you'll often hear coordinates referred to as Cartesian coordinates and coordinate geometry referred to as Cartesian geometry. It's just in homage to René Descartes, who was the first mathematician to actually write his formulas, well, represent his formulas graphically. And that only happened about 500 years ago, so it's quite interesting that mathematicians didn't think in terms of graphs up until relatively recently. Now, what we're going to be looking at in this presentation is very much the key ideas, and perhaps some of this presentation will be a little bit like teaching you how to suck eggs, and I hope that isn't the case. I will try and keep it brief, just as a little reminder of how coordinate geometry works. And I'd like to point out as well, when I'm delivering this, I like to start with just 2 points, just 2 coordinates, and then I go through with those 2 coordinates how you would find the distance between the points, the midpoint of the 2 coordinates, the gradient of the line that passes through the 2 coordinates, and then finally the equation of the line that passes through the 2 coordinates. What I would also add, if it was a very strong class in say year 10 or year 11, I would also show them how to find the equation of the perpendicular bisector through those coordinates. I'm going to attempt to do all those things for you now as well, just as a little reminder for how these things work. I like to show a numerical example first, and then come up with some generalizations, some formulae if you like, which we might use for any 2 points for finding the distance, midpoint, gradient, and the equation of the line. So, let's start with finding the distance between 2 points. And I'm going to simply use the word Pythagoras here. Now you can see I've given you 2 points here. One coordinate here has the one point has the coordinates 1, 6, so x equals 1 and y equals 6. The next point has the coordinates 3, 2. Now if we want to work out the distance between those 2 points, all we really need to do, and it's well worth drawing this on a whiteboard for the students to see, or perhaps with some graphing software, draw the right-angled triangle on there, and then hopefully you can convince them that no matter where you put the 2 points, you can always construct a right-angled triangle. I guess if the 2 points are exactly flat, or completely horizontal or vertical, you won't have a right-angled triangle. I mean, in essence, we call that a degenerate triangle actually at a higher level. But hopefully they can just see that the distance is the squares between them. But in most cases, we will have a right-angled triangle. And what we're looking for is the hypotenuse. And therefore, that is the reason why our formula for distance actually looks very, very similar to Pythagoras' theorem. So the distance is going to be the square root of how much you've changed there in the y-coordinate, which you can work out by doing 6 minus 2. So as you can see, the height of that triangle is going to be 4, and we're going to need to square that. So I do 6 minus 2 squared. And then we're also going to have to work out how far we go across on that triangle, and we're going to work that out by doing the x-coordinate minus the x-coordinate. So we'll need to do 3 minus 1 for that, and that will give us a gap of 2, and we'll need to square that. And then we simply add them together, and then try not to forget to square root at the end, because that is how we find the hypotenuse of a right-angled triangle using Pythagoras. And that gives me a distance of root 20, which I hope your students will tell you. I often leave it like that and just hope that one of them says, sir, can we not write that as 2 root 5? If they say that, I'm always very impressed, and I always say, oh, thank you for pointing out that I hadn't left it in its simplest form. But there you go, root 20 or 2 root 5 is absolutely correct. That is the exact value. You may want to work that out as a decimal. I'm not too interested in that for the moment. But that's distance. Next we come on to midpoint, And midpoint is in many ways the easiest idea to get across in a coordinate geometry session, because I think the midpoint works exactly as you would expect it to, because it is simply the middle of the x coordinates and the middle of the y's. Now the middle of 1 and 3 is clearly 2, so the midpoint's x coordinate will be 2, and the middle of 6 and 2 is simply 4, and therefore the y coordinates, the midpoint's y coordinate will be 4. That gives us a midpoint of 2, 4. And if you see on the diagram, if you think about where 2, 4 is, you can see it's slap bang in the middle, which is pretty convincing. Now the big question for me is, I often ask this to students, it's very easy to see the middle of 6 and 2, but what about if I had the numbers 3 and 97? What calculation would they need to do to find the middle of those two numbers? Now, hopefully, and this isn't so obvious, but hopefully someone will say, well, isn't the middle just the mean of those two numbers? Because indeed it is. So this is another way, if it's awkward to find the middle, you can simply add the two numbers together and divide by 2, and that will find you the middle of any two numbers. Next up is gradient. Now I'm sure you remember this. Gradient though, please never rush this topic. This is going to be coming up in the next presentation as well in far more detail and at a far higher level. But gradient is so important in maths, it really is. Gradient is a rate of change. It is the change in y divided by the change in x. And that word rate is super important. And they're going to be bringing that into the GCSE very, very soon. More questions involving the specific use of the language rate of change. That's very clear in the new specification. They're going to want students to understand that gradients are a rate of change. Well, in what sense is it a rate of change? Well, it's the rate of change of y with respect to x. That's why, if you think back to your A level, it is written as dy by dx, the change in y over the change in x. This idea of a rate pops up everywhere as well. I'm going to talk about it more in the next video, but just think about speed. Speed is a rate of change. It is meters per second. How many meters you travel in 1 second. That is a rate of change, which is a gradient. Anyway, in our situation, and when students first meet gradients, it's quite natural to teach it as rise over run. Yeah, how far you go up divided by how far you go across. Now they often get the sign of the gradient wrong, and it's relatively easy to get across what the sign should be if you just point out that if from left to right it goes down, it has a negative gradient, but if from left to right it goes up, then it has a positive gradient. That's probably the easiest way to consider it. But when they're working out the gradient, get them to draw a little triangle on. So that's what I've done here. I've drawn a little triangle on again, just like I did with distance, to point out it's similar to, you know, you want the triangle there to work out the gradient. Well, this one hasn't risen, it's actually fallen by 4, and that's why I've got -4 on the top of my gradient. And then the run is 2, we've actually gone across 2, so I've got -4 divided by 2, and therefore my gradient for this line is -2, and that is gradient. Let's have a look now at finding the equation of the line y equals mx plus c for that. That is a standard general result. It's something I would strongly advise the students to learn. That formula, the general equation of a straight line, y equals mx plus c. I'd like to point out that it's not the only way of writing down the equation of a straight line. We can of course have other formats. Another popular way of writing it is ax plus by plus c equals 0, where a, b and c are integers. So please don't get this idea that, you know, any equation of a straight line must start y equals, because that's not true. But it's just, if it does start y equals, then the coefficient of x will be your gradient, and the number on the end will be your y-intercept. And I'm sure you remember that. M is the gradient, c is the y-intercept. Okay, if we're trying to find the equation of the line going through 2 points, what we need is the gradient and the y-intercept, but sometimes you may not have the y-intercept. In my example here, you might be able to see that the y-intercept is 8, but let's pretend we didn't know that. Let's pretend all we knew were the points. Perhaps we haven't drawn it out or anything like that. It's still possible to work out the y-intercept, because remember, this equation is supposed to be true for every single point which lies on the line. So I'm going to begin with y equals mx plus c, and I'm going to substitute m for minus 2 because as we already worked out on the previous slide, the gradient is negative 2. That gives me y equals minus 2x plus c. Now what I can do is use either coordinate or any other point that I know lies on the line. I can plug that coordinate in and find the value of c. So what I'm going to do is use the coordinate 1, 6. So I'm going to plug in y is 6 when x is 1. Now weirdly enough, those kind of numbers swap over when you plug them into the equation, because 6 is obviously written on the right of the coordinate, but it'll be plugged into y, so y should be 6 and x should be 1. Plug it in and you will find c is 8, and therefore y equals minus 2x plus 8. And there it is, it's done. Now some of you will be aware that there is another formula for working out the equation of a straight line, and that is y minus y1 equals m times x minus x1. You can use that. There's nothing wrong with that, and I certainly teach that at A level, but at GCSE I think it's unnecessary, and I like them to use y equals mx plus c, and I don't want them to remember 50,000 formulae, or especially formulae which they don't necessarily need. So I just do it all from y equals mx plus c. And there we go. The equation of the line through those 2 points is y equals minus 2x plus 8. That makes a lot of sense because earlier we said the y-intercept was at positive 8. That so far is going to be pretty familiar to you. I'm hoping that the next slide might start to be quite useful because we can all forget things, and the next slide is going to be about finding the equation of the perpendicular bisector. First thing I want to point out is that a perpendicular bisector is simply a line which goes slap bang through the middle of 2 points and at 90 degrees, or perpendicular. Hence perpendicular bisector. Bisect because it cuts it in half, perpendicular because it's at right angles. So how are we going to find this? Well, we need two things. We need the midpoint, and if you remember we worked that out earlier. The midpoint is 2, 4. The reason we need the midpoint is because we always need a point on the line to find the equation of the line. Next up, we need the gradient of the perpendicular bisector, and for that we're going to have to use a new formula, or another formula, and it's the last one they really need in coordinate geometry. That formula is that two gradients multiply together to give minus 1 if they're perpendicular. Another way of looking at it is each gradient will be the negative reciprocal of the other. Now, because our original line had a gradient of minus 2, we're going to need to find the negative reciprocal of that, which means do minus 1 divided by that value, and minus 1 divided by minus 2 is in fact positive 1/2. And so the negative reciprocal of minus 2 is positive 1/2, and that gives us the gradient of our perpendicular bisector. Once we have that, we proceed exactly as before with y equals mx plus c, but this time we know that the gradient is 1/2, so we'll chuck in m as 1/2. We know that y is 4 when m is 2. We work the numbers through and we'll see that c is 3, and so we get the equation y equals 1/2x plus 3. Sure enough, on my diagram that looks absolutely correct because, yep, the y-intercept for the perpendicular bisector looks to be crossing at 3. We've got 2 points. Let's call our first point x1, y1, and our second point x2, y2. Let's decide what the general formula is firstly for midpoint. Well, all we need to do for midpoint is find the average, the mean value for the x's, because that will find us the middle with just two numbers, and the average of the y values. That gives me the formula x1 plus x2 over 2 for the x component of the coordinate, and y1 plus y2 over 2 for the y component of the coordinate. Next up is distance. Well, distance is simply going to be, think back to the distance problem, the numerical example, and if you remember rightly, we had to work out how much x has changed and how much y has changed to find the height and the width, if you like, of that right angled triangle. Next we'll need to square those values, add them together and square root them so that it is simply Pythagoras' theorem worked through. Next up is the gradient, and the gradient is simply the change in y over the change in x. Well, let's make sure then we just do y2 minus y1, that's the change in y, divided by x2 minus x1, that's the change in x. Next we have the formula for two gradients being perpendicular. That's simply m1 times m2 is minus 1. And the last one I want to remind you of course, is y equals mx plus c. It's a nice way, not the only way, but a nice way to represent a straight line. I like to show students a general formula. You may feel it's inappropriate with some of your classes, but I think it's a really good thing to do. But before I show them the general formulae, I always show them numerical examples, because I think, I always say to them, I don't remember these general formulae, I don't commit them to memory and then use them blindly. It's much easier if you understand it, then you have less to learn, and actually it's easier than using the formula. If you just draw the little triangle on, you can see where the formulas come from. But naturally you get some students who are formula junkies. If they are like that, then it will satisfy those students. Some students love to copy down a formula. Well, you've got to keep everyone happy, haven't you? But I always strongly advise them to really understand it rather than blindly using a formula. Okay, the last thing I want to talk about is inequalities and regions, or as I call it, pick a point, because if I ever want to decide which side of the line an inequality represents, all I have to do is pick a point to decide that. Now, I'm going to give you a little challenge here, and this is a bit more demanding than everything I've done so far, but still not much more really. It's pretty standard GCSE stuff. This is really just designed as a reminder, this presentation. Okay, I've given you a set of inequalities on the right. Y is less than x plus 3, y is greater than or equal to minus 3x plus 3, and y is greater than or equal to minus 4. And I've represented this on a graph, and you can see I've even taken the lines and given you the equations of the lines, which by the way you may be required to work out for yourself. But I wonder, can you find the region on that graph and label it for which the first three inequalities hold? And if you can manage that, can you try and do the same thing with the second set of inequalities? The next slide will show you the answers, but good luck. For the first set of inequalities, we've actually got the region to the right here, to the right of the green line, beneath the pink line and above the blue line. I hope I've got the colours right there. But yes, how can I tell that that region is given by those inequalities? Well, quite simply, as I described earlier, pick a point. Yeah, let's pick a point like, say, 4, 2, where x is 4 and y is 2. You will notice for that point where x is 4 and y is 2, that when I do, for example, x plus 3 and compare it to y, that x plus 3 is indeed bigger than y, because 4 plus 3 is indeed bigger than 2. It will be the same for the next two inequalities as well. Minus 3 times 4 plus 3 is less than or equal to 2. And minus 4 is obviously less than or equal to the value of 2 once again. So all three of those inequalities work for that point, and that's all you need to do to establish which side of the line is the side which represents a certain inequality. Pick a point and just see if it satisfies or doesn't satisfy the inequality. For the next region, if I pick the point 0, 0, which is always what I prefer to do because 0 is so easy to work with, you will see that 0 is less than 0 plus 3, so y is less than x plus 3. 0 is less than or equal to minus 3 times 0 plus 3, so that inequality is also holding. And then finally 0 is greater than or equal to minus 4, and so the last inequality is also holding. And so that little triangle in the middle is indeed the region which we would like. Now I just want to quickly mention before we finish, standard notation is that you dot a line if it is a strict inequality, but you make the line thick if it is allowed to be equal to. Yeah, so if it's a less than or equal to or greater than or equal to, you make the line thick. Back in my day at school, we used to actually label the lines line included or line excluded. I believe that is still absolutely fine if your students do that in the exam. But it is important to make it clear whether the line is representing a strict inequality or an inequality which allows you to include the line as well, an inequality which is less than or greater than or equal to. Okay, I hope that was just a reminder and that's helped you refresh your memory about coordinate geometry, because we're going to be using a lot of these ideas in the next presentation, but at a higher level. Thank you very much, and I will speak to you soon. Bye bye.